Hello and welcome back. In today's lecture, we are going to talk about distributions. In probability theory, there are numerous distributions. However, we are going to study distributions from a standpoint of a data scientist or data analyst. What are some of the most important distributions that a data scientist should know? Let us explore. What are the prerequisites of a probability distribution? You must be familiar with some of the terms such as experiment, random variable. What is an experiment in probability theory? A trial with a set of outcomes, whether those set is finite or infinite, is known as an experiment. The variable that denotes that experiment, that denotes the results of that experiment, is known as random variable. A random variable could be discrete or continuous. A discrete random variable takes discrete values such as 1, 2, apple, orange, the values which are discrete in nature, whereas continuous random variable could pick any value in a particular range. Before we proceed ahead, I have a chocolate problem for you. We shall definitely discuss this problem at the end of this lecture, but till then, let us keep exploring and make you keep thinking. Let us assume that team A and B are playing a game of tennis. They have to win at least 4 out of 7 rounds to win the game. The probability that A wins any round is P. What is the probability that they will play all the 7 rounds? Well, this might sound confusing, but I'm sure at the end of this lecture we would be able to solve the problem. Till then, let me know in the comments what are your thoughts. So, let us proceed further. What are the 5 probability distributions to know as a data scientist? Uniform distribution, Bernoulli distribution, binomial distribution, normal distribution, and Poisson distribution. The very first uniform distribution is the most basic in nature. By the term uniform, you would understand something which is uniform, right? Something which does not change in a particular range. For a uniform distribution has two parameters, the lower bound A and an upper bound B. The mean of uniform distribution is upper bound plus lower bound by 2. Okay. In a uniform distribution, the mean is equal to median. The next is Bernoulli distribution. The Bernoulli distribution represents outcomes in a true or false fashion. Any experiment with two possible outcomes, true or false, 0 or 1, heads or tails, could be represented by a Bernoulli distribution. There is only one parameter associated with a Bernoulli distribution, that is P, the probability of success. Since this is a probability, its value should lie between 0 and 1. And the median of this Bernoulli distribution is either 0 or 1 depending on the value of P. Next is binomial distribution. Binomial distribution is again a discrete probability distribution whose parameters are P, the probability of success, and N, the number of trials. By number of trials, we mean the number of independent experiments that we conduct for a particular task or a particular to get the set of outcomes. The mean of a binomial distribution is NP. Again, P, since being a probability, is between 0 and 1. The median is either seal or floor of NP. Going forward with the next distribution, normal distribution. The parameters of the normal distribution are mu, mean of the distribution, and sigma, standard deviation. Since we already know the mean is mu, and the median is equal to mean is equal to mode. If you are not sure what mode means the value which occurs the maximum time. The Poisson distribution. Poisson distribution has only one parameter, that is lambda, which denotes the rate. The mean of the Poisson distribution is lambda. We shall explore these distributions in further detail in the coming slides. Again, before going further to the details of those distributions, it is very crucial to learn about the expectation. Well, the expectation that one could have from a content creator to produce quality content, the expectation that I would have from you to like, share, and subscribe to the channel, the expectation that a parent have from its child, the expectation that a child has from his parents, the expectation that a girlfriend has from boyfriend, the expectation that boyfriend has from girlfriend. No, we are not talking about all those expectations. What we are talking about here is a weighted average or the generalization of weighted average. We know that weighted average, the one specific weighted average is mean. However, we are talking here about the generalized weighted average where the weight might be different for each of the possible values in the set. In the mean, each values in the set have the weight 1 or same weight. Arithmetic mean of a large number of independently selected outcomes. Cons- from the example, we can see that a random variable x with finite set of outcomes x1, x2, x3, and xn with probability occurrences p1, p2, p3 up till pn. What would be the expectation of this random variable x? It would be summation of x1, p1, x2, p2, x3, p3, so on up till xn pn, where x is a discrete random variable. If it had been a continuous random variable, we would take the integral like x fx dx, where fx is the probability distribution function which represents the area in a very small interval or like infinitesimally small interval. This is a separate concept which comes in higher standard mathematics, the concept of integral. We would not require to go into the details of it, but just understand this also represents summation in a continuous random variable. Some of the formulas associated are as you can see, the expectation of a function of x is a summation of that function of x multiplied by the probability of x for discrete, and again for continuous we have the integral gx fx dx. Expectation of x square is summation of x square px. Now we know that x square is a function of x, so gx px. I hope this is clear so far. Let us proceed further with some more properties of expectation. Now, expectation of two random variables, the summation of two random variables is expectation of x plus expectation of y. Expectation of a constant multiplied to a random variable is constant multiplied by expectation of x. Expectation of xy would be equal to expectation of x multiplied by expectation of y only if x and y are independent. Now, let us go through a problem. Can you make money from a casino? Let us see, especially from a roulette game. I doubt, but let us see by the problem. What is the expected return upon spending $1 in a game of roulette where you get 35 times the amount upon success? Okay, I hope the problem is clear. You are spending $1 to play one round of the game of roulette. The game of roulette is nothing but where you roll a ball and the ball lands in any one of the. Let me put up the image for you. See, this is the game of roulette, right? In the game of roulette you pick any number. Now if the ball lands on that number, you win a certain amount. Here you would win 35 times the original amount that you would invest. So say you are investing $1, you would get $35 if you win. Now what are your chances of success? Let us see from an expectation point of view. From an expectation point of view, now the probability of success would be 1 by 38 since the roulette has 38 possible outcomes. Expectation would be minus 1 since you are spending 1, so 1 times your probability of loss would be 37 by 38 plus x2, that is 35 winning, is the probability of which is 1 by 38. So overall you are going to make a loss of minus 2 by 38, that is minus 1 by 90. Now I'm sure you would know how these casinos make so much money. And next time before you go to play in such casinos, make sure what is the winning amount that you're getting and how can you improve your chances of winning. Uniform distribution. Uniform distribution is defined by upper bound and lower bound. It can be both continuous and discrete. The probability of occurrence of any outcome is equal to 1 by b minus a or 1 by total number of possible outcomes. Some of the examples of uniform distribution: probability of having a head or tail upon tossing a fair coin, probability of having 6 on the face of fair die upon rolling, probability of drawing a king of hearts from a deck of 52 cards. All these have uniform distributions because the probability of drawing any one outcome from the set is equal to the probability of any other outcome. Going further with the Bernoulli distribution. So in Bernoulli distribution, as we already discussed, we have two possible outcomes, either true, false, 0 or 1. We know the probability of success as p, so the probability of failure would be 1 minus p. It can be thought of as an experiment finding true false answers. Some examples of Bernoulli distribution: tossing a coin, possibility of raining today, roulette in a casino. Mean of an experiment following Bernoulli distribution is p. Variance is expectation of x square minus expectation of x whole square, which would come out to be p into 1 minus p. We can see from the formula below how the expectation of x square is p. Okay. Let us proceed further with binomial distribution. In binomial distribution is again a discrete probability distribution, right? Now, probability of k successes in n trials. Each trial is independent of any other trial. If the trials are not independent of each other, it would not be a binomial distribution. This is a very important requirement in a binomial distribution. Bernoulli distribution is a special case of binomial distribution where the number of trials is 1, right? Here also we have two possible outcomes. Outcome could be true or false. In addition, we repeat that experiment over n times and we try to find out the number of successes in those n trials. We represent the probability of having k successes in n trials as a formula depicted in the slide, where k represents the number of successes, n is the number of trials, k should be less than equal to n and greater than equal to 0. P is the probability of success. Okay. Expectation of x is equal to expectation of x1 plus x2 plus x3 plus xn. And since we know that all these experiments are independent of each other, which is a necessary and important condition for binomial distribution, we can represent them as expectation of x1 plus expectation of x2 plus expectation of x3 and so on, which would be nothing but expectations of each of the independent Bernoulli trials. Okay. Now each expectation of each of the Bernoulli trials over n times is n into p. The variance again would be n into p into 1 minus p. Again a problem for you. In a population of 100-watt light bulbs manufactured by a company, 80% or 0.8 as a proportion have lifetimes exceeding 800 hours. Say there are 100-watt bulbs, 100-watt light bulbs manufactured by a company, right? And the lifetime of those bulbs to exceed 800 hours in an average case is zero point 0.8. An inspector samples 10 bulbs at a random. So you're sampling 10 bulbs at a random, any 10 bulbs out of those set of population of bulbs. Now, what is the probability that all 10 bulbs lifetimes exceed 800 hours, right? Now, you have to find the probability of those 10 bulbs to exceed 800 hours. First of all, if the problem sounds confusing to you, look at what are the given hints. So, what are the hints that we can find? We know that the probability of success in any one case for selecting any one bulb is zero point 0.8, right? What other information do we have? We have the number of items in the sample, that is 10. What we have to find? We have to find that probability of success being 10 in the sample of 10. How do we find it? But before that, do you understand that that probability of any bulb having a lifetime of 800 hours or more is independent of the probability of any other bulb? So this is an independent trial as well. Now, this being an independent trial, having the number of successes required, having the probability of success is nothing but a problem of binomial distribution. Now let us apply the formula. So you see that we have n as 10, probability of success is 0.8, k as 10. Each bulb's lifetime is independent of any other bulb from the given parameters. Therefore, it is a binomial distribution. It follows binomial distribution, and the result could be obtained by putting into the formula, which is seen as here in the next slide. So, go through the problem once again if you find it confusing or if you find some doubts here. Feel free to mention in the comment if you want more explanation or more details about the problem, and always try to solve it on your own before proceeding to the solution. Next up, we shall explore the next distribution as normal distribution. So normal distribution is the most widely available distributions in our real life. In all our day-to-day activities, most of the distributions that we see around us are normally distributed. There is a very separate theory about it, why we have distributions as normally separated and not any other distribution, and that is covered as central limit theorem, which is covered as part of a separate video whose link would be present in the I button above, right? But just to give you an idea, if from a population you take out a sample, randomly take out a sample, and if that sample size is large enough, say the sample size is more than 30 or equal to 30, then the mean of such samples, you would pick out many such samples, then the mean of those samples would be normally distributed. This is what central limit theorem presents. Next is, in a normal distribution, it is a continuous probability distribution whose probability distribution function is given by the function fx as shown in the slide. One very important attribute of normal distribution is 68% of values drawn from a normal distribution are within one standard deviation away from the mean. So you see that here the mean is 0. One standard deviation would be sigma times to the left and sigma to the right, right here, right? So 68% of all values would be available in within one standard deviation. This holds true for all normal distributions. Next is, about 95% of the values lie within two standard deviations and 99.7% of the values within three standard deviations. This is also known as 68, 95, 99.7 empirical rule, or the 3 sigma rule. So next time when someone asks you what is 3 sigma rule, let them know that you know the answer already. A question now. A radar unit is used to measure speeds of cars on a motorway. The speeds are normally distributed with a mean of 90 km per hour and a standard deviation of 10 km per hour. What is the probability that a car picked at random is traveling at more than 100 km per hour? Okay, so very interesting problem. First of all, try to solve the problem on your own before proceeding to the solution, right? Take a pause here, solve the problem, and then proceed ahead. Let us go to the hints. What are the available information that we have? We have mean. It is already mentioned that this is a normally distributed, so we know it's a normal distribution. Mean is 90 kilometers, standard deviation is 10 kilometer. We want to find out what is the probability of x being more than 100 kilometer. So first of all, in a normal distribution, we try to convert any normal distribution to a standard normal distribution. Why do we do that? Because standard normal distributions are because normal distributions themselves are so widely studied that their values have been standardized and computed. So for a standard normal distribution would have a mean of 0 and standard deviation of 1. Any normal distribution can be converted to a standard normal distribution, and the values can be directly found. The values of the area present within a particular range of the standard normal is presented as a standard normal table. We see that table as well. So we first compute the standard normal z corresponding to x. Here we have x as 100 kilometer. So standard normal would be 100 minus the mean 90 divided by the sigma 10. So 100 minus 90 is 10, 10 by 10 is 1. So z is 1. We have to find probability of z greater than 1, or the total area greater than z equal to 1, where in this chart if you look at, this normal distribution, this is a standard normal distribution, the mean is 0, standard deviation is 1. We have to find the green port marked area, right? So on the right you have a standard normal table which can be read as the values of z, or the area contained between the mean 0 and the value of z. For example, here we are getting the area z of z equal to 1, which is 0.3413. If we go to the row where 1 is there, we see the value is 0.3413, which is marked as orange. We have to find out the area of the green region. So how can we find? We know that the total area is 1. If we subtract the area of this orange region and this white region on the left, to the left of mean 0, right, we would have the area which we have to subtract from 1, right? Hope this makes sense. So let us see, the total area is 1, the area between the mean 0 and z equal to 1 is 0.3413. The area to the left of the mean 0 is zero point 0.5 because the normal distribution is symmetric. So we will get the final area of z greater than 1, which would be our probability. Hope that makes sense and gives you a very clear picture of how normal distribution and why standard normal distribution. Next is the Poisson distribution. Poisson distributions are again one of the most widely studied distributions in probability theory. Poisson distributions are represented by only one parameter, that is rate. It is a discrete probability distribution and it represents the probability of a given number of events occurring in a fixed time interval. Previously, in binomial distribution, we were computing the probability of case successes in n trials. Now we are limiting our time. We are not limiting the number of trials. We are limiting our time, and we want to find out how many such events occur in that time frame. Examples of Poisson distribution: probability of 100 cars crossing a signal in next 10 minutes. Probability of 20 calls received in a call center in the next 1 hour. Probability mass function of the Poisson distribution is represented as in the figure here. Expectation is equal to the variance is equals to lambda. Given the average rate r, say for example we have the average rate r, rate with time, we would have lambda which is equal to r into the time period. Again, going to the applications of Poisson distribution, suppose on average one guest arrives in your house every 3 months. What is the probability that no guest will arrive in the next 3 months? On an average, one guest is arriving in your house every 3 months. What is the probability that no guest will arrive in the next 3 months? Pause the video here. Let me know what the solution is. What are the hints? Rate of arrival of guests every 3 months is 1, which is lambda. We need to identify the probability of x equal to 0 since we don't want any guest. Since we have the rate specified, it is noteworthy that the above problem follows a Poisson distribution. If we plug the formula of lambda into the solution, which is lambda is 1, we plug the value of k, which is 0, we would get the resultant value of probability x equal to 0. Note that 0 factorial is equal to 1. Okay, so this would be the final solution. Okay, the value of e is approximately taken as 2.7182818. Now coming to our chocolate problem, which I gave you as a task on the very first. If you have been able to solve the problem, that's absolutely good. Even if you haven't, we shall see how this problem could be solved, so that in the coming future you would be able to solve such problems on your own. So the problem was, team A and B are playing a game of tennis. They have to win at least 4 out of 7 rounds to win the game. The probability that A wins any round is P. What is the probability that the game will be played up to 7 rounds? So if any one side wins 4 games, the game ends there. And you have to win at least 4 rounds. Okay. So in order for 7 rounds to be played, each side must have the same score at the end of the 6th round. Obviously, if any one side would have more, then they are already winning and the game would end there. However, in order that the seventh round to be played, each side would need to have the same number of same score at the end of the sixth round. So here let us assume that k, which denotes the probability of successes of A, would be 3. Obviously, if each side has to win the equal number of rounds and total rounds is 6, so each side would have won 3 rounds. It does not matter the order in which they won, it's just that the number that's necessary. The n would be 6. So we have the probability of success, we have k, which is 3. Outcome of any round is independent of any other round. Now applying the binomial theorem, we plug into the formula which is available on the right, that probability of k, nk, which is the combination of nk, which mathematically is represented as n factorial by k factorial by n minus k factorial to the multiplied by p to the power k into 1 minus p to the power n minus k. If we plug into the values here, we would get the solution something as this. So thank you for watching the lecture so far. Hope you learned something new. Subscribe to the channel. Let me know in the comments what are your thoughts and what would you like the next topic would be. And let me know what can be improved to make the content more valuable, more informative, and much more better informed. Thank you. Bye bye.